Alright, ladies and gentlemen, so in this video we are going to look at a great topic of compound interest. Alright, very fun topic to deal with personal finance. A lot of it does, at least. Not all of it, but a lot of it does, and a lot of things that we deal with in everyday life. Have to deal with some compound interest and things like that. We talk about investments and things of the nature as well. So let's take a look and kind of think about what to look forward to in this video. And so in our last video, we dove into the law of exponential change, and we did a basic definition and a basic example as to how to take some information in terms of a growth constant or a decay constant and put it on into a good formula or a good equation for technically a differential equation that will allow us to see some possible growth or decay depending on whatever we're talking about, right? And so in this video, we're going to look into some real-world applications involving continuously compounded interest. So let's dive right on in. So we might remember the formula if we are going to compound a particular investment, all right? You hear the bankers say a lot compounded instead of added. That's kind of banker terminology. And so if we compounded our interest over a certain amount of time. So whether it's 12 times a year, that would be monthly, right? Or if it was weekly, it'd be 52 times a year, or even daily, 365. And we looked at if you had A of T being your investment, A naught, I, or P would be the initial principal, multiplied by 1 for the first time that you had it, plus your rate divided by however many times you compound it throughout the year, times that same constant for however many years you plan on doing it T, right? But then we've also looked into, well, what if we didn't want to just do it over a discrete interval, right? And what if the interest was added continuously at a rate proportional to the amount in the account? We can model this growth, all right, with a new formula. And you've seen the formula before for when we want to make it a proportional amount to continuously compound it itself. Sorry about the pause, someone coming in my classroom, and so now what happens if you want to continuously compound it? And this is the good stuff happening, guys. So if we want to compound continuously, we look at our great formula, A of T equals A naught E to the RT. You may have also heard this as the PERT formula before, right? Your initial principal times your exponential times your to the rate times T, okay? And so the number R is known as the continuous interest rate that you will get. So let's take a look here at some options and some examples for the following. So let's take a look. Let's say we have this following situation. Suppose you deposit $800 in an account that pays 6.3% annual interest. All right, not a bad investment. All right, you could have done a better investment in 2017. The S&P 500 actually averaged about 19.4% interest. You would have made 20% on your investments in 2017, and hopefully that happens in 2018 as well too. And so there's some things to look forward to, guys, when you get out of high school and out of college into the real world as well too. Get yourself debt free and get some money to invest. Now, this can be some good stuff, and it teaches you a lot, just like we have here. How much will you have 8 years later if the interest is 1, compounded continuously, and 2, compounded quarterly? So let's take an interest here. So we initially have $800 thrown into account. That's our P. It's our A sub naught, or our P, our initial principal that we are throwing on into it here. So A of T is equal to A sub naught. I want it continuously, so that is our E to the RT. Alright, so A of T, well, T in this case is 8. And that's going to equal our initial investment of $800 times the exponential. And we have an interest rate of 6.3. And so that's going to be shown as 0.063 times our time value of 8 in this case. And throwing this on into the calculator, we see that we roughly look at about 1,324 and 26 cents. Okay? So let's take a look here if we compound it quarterly. Alright? Quarterly. And so in a situation here, we have A of T, but now we want quarterly. So now we're going to look at A naught, or our initial principal, times 1 plus our rate over K times or to the constant times T. Well, once again, we have our time value of 8, our initial value of 800, times 1 plus our rate, 0.063, over our constant, and it's quarterly, so out of many times in a year, that would be 4 to the 4 times 8 power here. And so using our PEMDAS and throwing in the calculator, we end up with a dollar amount of $1,319.07 here. Okay? So kind of interestingly put, I mean, personally, I would have expected to see a little bit more growth, compounding continuously over an 8-year span. But again, it's one thing to kind of see the difference in here versus, compounding it 4 times a year versus continuously with the proportional rate of change happening on in there. Okay, so there's an example of using our compound interest. We're going to look into radioactivity and half-life in our next couple examples here.